Hello friends. In this group of set of lectures, I want to talk about linear algebra, especially basis. I split linear algebra into three pieces. One concerning about basis, that is what we are going to see now. In my intro lecture, I explained what kind of way I am going to do that. Okay, so I really do not want to start with basis. Sorry, I mean, what is the definition of vector space? Okay, I wanted to start with very concretely about basis, and so that my main aim is to attack problem. So more and more problems. Okay, so I am doing linear algebra because it has a very great connection with many subjects. Especially I wanted to do Galois theory later. For that I needed this essential linear algebra. Every video we will kind of spend little bit about definitions, insights and other things. Okay, so the main idea, we will consider more definition, the point of views like that. Okay, I will start with linearly independentness and linearly dependentness. Okay, we will see what is really that. Okay, for me always F field and V is vector space over field. This you can see in Vishwakumar sir lecture about definition of field and definition of vector space and definition of linear transformation. Okay, now what I am going to do, okay, let's start with the definition slowly. Linearly independence. Linearly independent. Okay, what do you mean by linearly independent? Okay, I have a subset yes contained in V. I did not say it is empty or nothing. So to be linearly independent if whenever, this is very important, I will explain why this is. That's why I am not assuming this is not empty or non-empty. Whenever alpha 1 v1 plus dot 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 alpha n vn equal to 0, where alpha is belongs to the field and vi belongs to the set yes, then that implies alpha I is equal to 0 for every I 1 less than or equal to n. Okay, I will explain now why this is so. First of all, I didn't assume here this is empty or non-empty. Okay, remember that the word whenever, this is very important. You see, whenever this is happening and I like to say that each alpha equal to 0, then we call this is linearly independent. Okay, so empty set is linearly independent. For example, you take empty set S equal to empty set, and it is linearly independent because to show it is linearly dependent, so that if it is not satisfying, I wanted to show there exist vi's I1 equal to n in S such that there exists alpha is belongs to F summation alpha I vi equal to 0, but there exists I such I naught, let's say, such that alpha I not equal to 0, which I cannot show here because I cannot take such collection here because it is empty. So my definition says that empty sets always linearly independent. This is very important. The whenever, this word is very important. Okay, so to show something is linearly dependent, what one wanted to show really, there we have to take collection of these things vi's, and we want to show there exists alpha in from the field, and this is happening. So that's why this word is very important. That's why I'm really spending time on this, because one should get very clearly adopt these definitions so that one can go through very well. Okay, this is very important. Again, I'm telling that whenever I'm going to say a subset is linearly independent if whenever this happen, whenever if it is happening, then I have to show this thing. I want to say something is linearly dependent, then I wanted to show the existence. From here it's very clear that S equal to empty which is linearly independent in any vector spaces. Okay, vector space is not empty because it's basically a group. Then it has extra condition. Okay, field is also not empty. So let's see about spanning. Definition of spanning. I will give you two equivalent definition, and one should see why this is equivalent. One condition, the spanning is like this thing. Let's say let V be a vector space over F. We say S contained in V spans V if every vector belongs to V can be written as linear combination of vectors in S. That is, every vector belongs V, there exists alpha i's belongs to F and Vi belongs to S. V equal to summation alpha A and Va, and this is called linear combination. Okay, this is very important. The word is very important, linear combination. Okay, this is one definition. Another definition is a general thing. Let S contained in V. I will take this is called spanning. Okay, this is called spanning. So what I like to say that this it's a smallest vector space which containing S. In other words, intersection of all, I will make it clearer once. I'm saying the intersection of all subspaces of V which containing S. Okay, it's like smallest vector space containing S inside V. It's like that. Okay, like, okay, I will say like that. Intersection of all W is a subspace of V and S contained in that. So S contained in W is a subspace. So one should see this both conditions are equivalent, and that is exercise. I will let you to do that, and you see both conditions are very extremely important. Okay, whenever S inside is some space, that implies W. In fact, if and only if, because S is always inside here. So this is a condition. Okay, so with these two definition, let me give you the definition of basis. What is basis? So S contained in V is said to be basis if S is linearly independent, basis of V independent set. Second, S spans entire V. That means, and we will see in next few lectures about this basis, and we will see the characterization of the basis, and after that everything will be clear. We will get habituated with the basis definition. Okay, in the next lecture we will see. But I wanted to make sure another word, order. What is ordered? Suppose I have a basis, let's say non-empty basis, then I wanted to order these elements V1, V2, Vn. Okay, if it is finite and this is like order in a natural number, infinite, countable infinite, we can order by natural number. Or if it is like uncountable, we will use some order. Okay, we will like order the linear some order. Okay, but mostly I am going to deal with the finite dimensional vector space, so I will order like this. So I don't really care about infinite dimensional right now, and but most of the things will work out with the infinite dimensional. Okay, here also I mentioned Vi is like 1 to n finite collection, finite linear combination, not an infinite linear combination, not like a Fourier series. Okay, It's very important to distinguish those things. Okay, and we will see about basis and other thing, few properties of basis and spanning in the next lecture.